Asif sir, welcome sir.
Is it better now? I've changed the date.
Yes sir. Yeah.
The complete screen is visible, right?
Yes sir,
Yeah,
visible. Yeah.
your entire PPT is visible.
Okay. Should I unshare now?
You can keep it on.
I
You
can
can keep
keep
it
it?
like this. Yeah.
Okay. Okay.
Just one more minute. We'll start in a minute.
Okay. Anusia, let me know when we have to start.
Sure. Shall I start now? Yeah.
Ma'am, shall we start, ma'am?
Yes, absolutely.
Yes, ma'am.
We welcome you all to this IEEE lecture series on quantum computing. This lecture is organized by the IEEE Students Chapter in Electrical Department, Vardhaman College of Engineering, Hyderabad, and it is my privilege to introduce the speaker, Dr. Ankur Raina, who is an assistant professor in ISER Bhopal. Dr. Raina has worked previously in the University of Arizona, USA, and before that he completed his PhD research in quantum computing from IISc Bangalore. He has a broad range of interests in this field, including classical and quantum information theory and coding, quantum optics, quantum cryptography, quantum algorithms, fault tolerant quantum computation. In fact, he has already introduced us to the quantum domain last week where the laws defy our everyday perception and logic. Qubits, which are how information is stored in the quantum domain, they can be changed on Earth and can be received in Pluto, and the normal limitations of space-time does not seem to apply in this arena. So this is a very interesting topic, and today he will give further insights into this field, which is considered one of the frontier areas of science. Without any more delay, I invite Dr. Ankur Raina to present his talk. Please, sir.
Thank you, Dr. Anusaya, for this wonderful introduction. Made my day. Thank you so much. So what we're going to do today is, continue from what we discussed last time. And if from the feedback that I received, I think I'll cover a little bit more in terms of the basics today, so that it gives us a strong foundation for the rest of the talk. Okay. All right. So let's quickly recap what we did last time. This is the outline of the talk we have. We started with why quantum laws have to be invoked. Why do we have to be interested in them? Mainly, it is because of the shrinking of the devices. Mainly, the memory devices are becoming smaller and smaller. The storage density is increasing, and because of the Moore's law, we expect more number of transistors to fit in the same area, and roughly the number of transistors double every 12 to 18 months or so. So we expect at some point of time, close to maybe 2025 or 2030, we expect that the storage density is going to be so huge that we will have to store at the level of an atom. In terms of numbers, maybe 1 bit would have to be stored in 1 atom, because that kind of density is being expected or projected. So when we enter the realms of atoms which are very small, we have to consider the new laws. The traditional Boolean laws no longer hold. The Boolean laws are such that above a certain voltage or current, you call it a logical 1, and below a certain threshold you call it a logical 0. So the same laws won't be applicable, uh, and this invites us to explore new ways of expressing the same phenomena which is happening at the level of the atom, and that those laws are the quantum laws. So to make sense of what is happening at the at the level of atoms at those sizes, we took an example of a double slit experiment where we initially said, okay, if you consider a light source, there's constructive and destructive interference happening on the screen, and it is because of the wave nature of the light. And then later on, some scientists considered the electrons being shot from an electron gun. Now, traditionally, you would believe that the electrons are particles, and you wouldn't expect interference pattern, but it turns out that we do have interference pattern, and the reason that we see this, or we observe this kind of a phenomena or an observation, is because the electrons also behave as waves. So this is something which is counterintuitive, because particles, you tend to believe that behind the slits that the electrons will accumulate, and you would expect dark patches behind just the slits, but we observe that there's going to be an interference pattern. So some scientists thought about it, and namely it was Dirac who gave the mathematical representation, saying, okay, if we have to look at it from the way we have known or observed science, you can think about the electron being present at the two slits simultaneously. It's going through the two slits simultaneously. This is not what you would see or observe in a in a natural phenomena. For example, if you're in your everyday life, you don't expect to be at the same time in two different places. You don't expect to be in this talk as well as at home, or maybe office and home at the same time. You don't expect that kind of a phenomenon, but here we are seeing that kind of a phenomena. All right, so mathematically put, we can define a quantum bit. A quantum bit is the quantum analog of a classical bit. A classical bit is either a 0 or a 1. However, a quantum bit can be seen as a vector now, a two-level system where you have two components in the vector, and you represent the state of a quantum bit using some column vectors. And how do we express a column vector? We use some basis vectors, namely 1, 0, and 0, 1. You can think about this as a as the x-axis and the y-axis. For example, if you have to consider any point, let's say 3, 4. 3, 4 is made up of 3 times the unit vector along the x-axis and 4 times the unit vector along the y-axis. So the unit vector along the x-axis now gets sort of promoted, and you can call it as a column vector 1, 0. It's basically the same. The unit vector is now 1, 0, and the unit vectors are namely 1, 0, and 0, 1. So you can express any point using these two basis vectors. Now the extension that you can think of from the xy plane is that on the xy plane you have this point 3, 4, but both of these are real numbers. So the major deviation here is that now these two these points, namely let's say some a comma b, a can be a complex number and b can be a complex number. So when we have a column vector ab that you're seeing here, let's say this is a0 plus b1. Basically, it means there is a column vector ab, and a and b can themselves be complex numbers. Okay, so that is the deviation we have from let's say an xy plane. So we use these basis vectors to represent any point. So here every point here refers to a state or a column vector. Now you can think about it in a colloquial language. If I have to write what does this basis vector actually mean? For example, if you have to say how to express the weather of Bangalore, so you will consider extreme heat as one of the basis vector and extreme cold as another basis vector. So you can think about the weather of Bangalore to be, let's say, half of extreme cold, or and plus half of extreme hot. So you can say half of maybe so Sahara Desert and half of let's say Siberia. Something like this can be used. So these factors, these coefficients are going to scale whether how close you are to very extreme weather or how close you are to extreme hot weather. So something like this to make sense of what are these column vectors, what are these basis vectors. Basis vectors are basically how to they are the like unit vectors that we have seen so far, like I hat, j hat, k hat, all those things that we have seen so far. And it's just an extension where we use, instead of I hat, you just use column vector 1, 0, and j hat, you use the column vector 0, 1. So any column vector can now be written as a combination of a times the basis vector 0 and b times the basis vector 1. All right, so this was a quantum bit. Basically, it's a state. It is represented by a state, and it allows for the principle of superposition. What does it mean? Superposition means that it is both 0 and 1 at the same time, and the information is physical, that you can store information in the properties like angular momentum, polarization. All these things you can use to store information because these properties are inherently representative of the quantum bit. Yeah, in the sense that this polarization can be seen as column vectors 1, 0 or column vector 0, 1. For example, in the horizontal polarized photon can be seen as 1, 0, and the vertically polarized photon can be seen as 0, 1. So the actual physics is corresponding to the math. So there's a good synergy between what is observed in physics and how it is written mathematically. That's how this whole branch came about. And this physics now allows us to manipulate information. Now, when you're manipulating information, the states are going to change. What is the mathematics? The mathematics is basically linear algebra, and the way these states change is basically how these column vectors change, and it's all linear here. Okay, and this, the physics gives us opportunities for secrecy and communication. So there were some postulates that we considered in the previous class. I'll just run through them. How are we doing on time? Okay, so 15 minutes. Okay, so basically the states that we consider, or the column vectors, are unit vectors, and we have some vector space. The vector is lying in that vector space, and each vector is representing the state of a quantum bit. So you have this column vector AB, and this is lying in some vector space. And how does this evolve? This is evolving through a unitary evolution. So you have AB, and then it evolves unitarily to some other state. And this unitary property preserves the length of the vector. And then there's a third postulate, that is measurement. When you do measurement, there is a change in the state. So this is something which is not seen in the classical world, where the act of measurement changes the very state of the state of a quantum bit. So this was the summary. Basically, a qubit is characterized by its state. Qubits can be treated by mathematical expressions, and you have a superposition principle where you have it is both 0 and 1 at the same time. And this is a column vector. So this is a ket, which represents a column vector. The conjugate, the complex conjugate, is the bra. It's a row vector. So you have a bar, b bar. And for any states, let's say a column vector psi and the column vector phi. So the ket psi and ket phi, you can write ket psi times the bra psi. This is a column vector times a row vector. So this gives us a matrix. And if we flip the other way, a row vector times a column vector is a scalar. And a qubit whose state is represented by psi is in superposition of 0 and 1. So that is the language you use. When you go to a new arena, you have to like adhere to the rules, new rules. So the language that is spoken is that the state is simultaneously 0 and 1, or you can say that it's a superposition of 0 and 1. And then there's the measurement postulate. Suppose the state is a0 plus b1, and you measure the spin, let's say in the z direction, then it's also called measurement in the 0, 1 basis, because we're going to cover that soon. If you remember from previous lecture, there was a matrix called the Z matrix, whose eigenstates or eigenvectors are namely the column vectors 0, 1 and 1, 0. And when you measure the spin in the Z direction, you're basically measuring the eigenbasis of that vector, of that matrix, and the state is going to collapse to either the column vector 0 or column vector 1, and the probabilities are mod a square and mod b square. And we can say that we have measured in the 0, 1 basis. You can of course measure in different bases. Then if you measure in the different bases, then the state will collapse to corresponding eigen states, or that or the quantity that you're measuring. So if you have a state psi and you're measuring the you're measuring some observable. So I'll try to use some terms, but that's how we have to use. So there is this, for example, there's a matrix. It's a Hermitian matrix. Namely, what it means is it's a matrix whose complex conjugate is equal to itself, and it has eigenstates, namely E1, E2 through En. When you measure this kind of a matrix or observable, then the state collapses to one of the eigenstates. So what it means is you have a psi, it's a qubit, and it's prepared in the state psi, and you're measuring let's say some operator or some observable whose eigenstates are E1, E2 through En. So what happens is when you measure this particular entity or the operator, the state, the psi collapses to one of the eigenstates, namely either E1 or E2 or En. So it collapses, this qubit collapses to one of these eigenstates with a certain probability, namely the you can call it lambda k. Lambda k is the eigenvalue of that particular operator. So it means that uh, the eigenvalue lambda1 has a corresponding eigenstate E1, lambda2 has E2, and lambda n has En. So when the state collapses to one of these eigenstate, it occurs with that particular eigenvalue. The probability is exactly equal to the eigenvalue. Okay, so this and then I think I sorry. So what I was saying is that you observe this lambda k on this. Suppose there is this device and you observe lambda1 or lambda2 or lambda n, and it occurs with probability given by the inner product of the square of the inner product psi and ek. So I think I was not able to say that first in the immediately. So but now I'm saying it. So you have a meter, for example, there's a device and it has this needle and it points to either lambda1 or lambda2 or lambda n. And whenever you see lambda, let's say lambda2, you infer that the state has collapsed to E2. And what is the probability that it collapses to E2? Collapses to E2. It is that mod inner product psi and ek square. So the psi collapses to one of the eigenstates with certain probability, and what do you observe on that device, on that meter, is the eigenvalue. So when you see the eigenvalue, you realize or you infer that the state has collapsed to the corresponding eigenstate. So this is just the mathematics. So for example, there is an observable, it's a Hermitian matrix. It has this decomposition. When you have a state psi and you're measuring this operator or observable O, you see lambda k. So on that device with probability given by mod psi ek square. Okay, and when you see lambda k, the state has collapsed to ek. So this collapse is instantaneous. Now what happens when you have multiple qubits? Just like you have classical bits, you have registers, and then you have bits, kilobytes, megabytes, all that. Similarly, you would expect that this quantum bits will also have that kind of a quantum register, but the growth is exponential here. For example, if you have n equal to 500, then we can perform computation on 2 to the 500 numbers all in parallel, all simultaneously. This is not possible in classical. In classical, you would have to do this first 500, then again 500, and again 500 and all that. But in quantum, all of these 2 to the 500 computations can be done simultaneously. But the problem is when you have to retrieve or read, you have to measure the quantum register. And in that case, you will just have to then what will happen is that the state will collapse to one of those 500 numbers and you have 500 numbers to work with. So what you can do is essentially the power of quantum computation comes where you have initially a classical problem, you have everything in classical, and then go to the quantum domain, do everything in parallel, this huge number, or the advantage that you get, do that in quantum and then come back to classical. So that is how we can expect quantum computing to fit in the current era, where we have already established the classical computation. It is going very well. So how do I fit the quantum? You will have to have an intermediate sort of a hybrid system where you have a classical, then it feeds to a quantum. You do all the processes simultaneously, and then you will have to do the circuitry in such a way that the result comes with a high probability, because the measurement is probabilistic and you want the desired result to come with a high probability. So to put it in very simple terms, let's say you want to add two numbers A and B and you want to use quantum computing for that. So what you would do is you take A and B and then take to the quantum world, then do the summation, whatever, and then you want the A plus B to come with high probability. When you measure, you expect the result to come with probability 1. You don't want A and B, and then you don't want to get the different result. So A plus B should be the outcome of the measurement with probability 1 or very high probability. So that is how you can think about or envisage how the quantum computing is going to be used. This was just a very trivial toy example that I said, adding two numbers A and B. Now, the state of multiple qubits resides in a space obtained by the tensor product of the individual spaces. So what I mean is there's this quantum bit 1, which is whose state is in some vector space, and then you have another qubit whose state is in another vector space. How do I sort of reconcile uh, uh, the vector space of the two qubits taken together? So for that, we need a tensor product. We need to operate on those vector spaces, and the mathematical operation is that of tensor product. So you take the tensor product of individual vector spaces, and that gives us the vector space of the total state of the multiple qubits. So if psi1, psi2 through psi n are the states of qubits 1 through n, the final state is going to be the tensor product of the individual states. So typically for qubits, you consider complex vector space C2, where, as I said, A comma B is a column vector, and A and B are both complex numbers. So that's why C2. So let's consider an example where we have two states, psi1 and psi2, and you want to find the state of the two qubits taken together. So for that, you just take the tensor product. So 0 tensored with 0, 0 tensored with 1, 1 tensored with 0, 1 tensored with 1 are now the new basis vectors of this larger vector space, and you need those basis vectors to represent the state of this two qubits taken together. So what is entanglement? This is one of the most exhaustive or most used phenomena in quantum computing. Is there's a special state. Let's say consider this column vector psi ab is its state given by 0 tensored 0 plus 1 tensored 1 by root 2. Then what happens is if you measure the qubit on system A in a certain basis, you can either get 0 or 1, right? That's how you are measuring. But what happens is, interestingly, the state of qubit B also follows what is happening with A. If the state of A collapses to 0, then the state of B will also collapse to a state 0. Same happens with state 1. So, but the probability with which you expect 0 or 1 is basically half. It's like tossing a coin. But nevertheless, whatever happens with A happens with B also. So this is kind of a superluminal communication may be happening that violates the special theory of relativity, but there's no communication happening because this is probabilistic. It's not in your hand, right? When you're measuring measuring the qubit A in certain basis, the outcomes are probabilistic. So that is not in your hand, but when you want to communicate, you want to send a deterministic signal, right? You want to send some useful information, but that is not happening here. It's all probabilistic. So there's no violation here. It's just that there's shared randomness. So in the sense that both are the measurement outcomes at A are random, but the same happens at B also. So they're together like this twins. Whatever happens with A happens with B. Another way of saying that or explaining this phenomenon of entanglement is that we know the nature or the state of the two qubits taken together, but we do not know what is the state of individual qubits with what do you say? We know it for sure. So we don't know the state of A and B for sure, but we know the state of two qubits together. So that's one way of explaining entanglement. You know the joint picture. You know the joint state well, but you do not know the individual states, the state of A or B individually. So they have a joint identity. In speaking in simple loose words, they have a joint identity, but they do not have individual identities. So something like this. Now Einstein called this spooky action at a distance because no matter how far they are, whether they are between Earth or some other planet, whatever is happening at A, same replicates at B. This is the phenomenon of entanglement. Now, how is quantum information processed? So what is quantum information? It's basically quantum states. You have column vectors and all that. And you need some gates to do some processing, right? You have similar to the classical world where you have AND gate, NAND gate, NOR gate, all that. Similar to them, we have quantum gates. So for n qubit state, so you have a state, that is giving the description of n qubits. Now the action of a unitary on this n qubit state dictates how the state evolves, right? Because the state evolution has to be unitary. For a qubit, for n qubit state, the unitary has to be of the size 2 to the n times 2 to the n, because you have 2 to the n entries in the vector, in the column vector, you have 2 to the n entries. So you have to have a unitary matrix U, which is of size 2 to the n by 2 to the n. Now U in general need not be a tensor product of matrices of smaller size. What I mean is this U need not be U0 tensor U1 tensor UN minus 1. So if it is of this form, then what will happen is U0 acts on the first qubit whose state is I0. U1 acts on I1 whose state is I1. So and UN minus 1 acts on the n minus 1th qubit whose state is IN minus 1. So you can write the description of this big huge U on the individual states I0, I1, IN minus 1. So you can think of this I0, IN, I1, IN minus 1 as a quantum register where the information in each like information storage is I0, I1, IN minus 1, and so on and so forth. So that's about quantum gates. What are similar to the standard gates in the classical world, we have standard quantum gates. In the quantum domain, we have the Hadamard gate. So what it does, it takes the state 0 and outputs a uniform superposition of 0 and 1 by 0 and 1, and it takes 1. It also gives a uniform superposition, but there's a minus sign. Similar to the NOT gate in classical, we have a NOT gate in quantum. What does classical NOT gate do? It takes 0 to 1 and 1 to 0. Similarly, here we have the quantum 0, namely the column vector 1 0, representing the ket 0. So the ket 0 should go to ket 1, ket 1 should go to ket 0. Similar to the now this is new. This is not happening in classical. You have the Z gate. What it does, it takes 0 to 0 and 1 to a minus 1. So there's an additional phase of minus 1 that gets introduced whenever there's a ket 1. And there's another gate called the Y gate. It takes 0 to I1. I is the imaginary number, and 1 is minus I0. So why are we saying the action of the gate on 0 or 1? Because 0 and 1 form the eigen states, or form the basis states. So the gate, whenever it acts on basis states, you can express the action of the gate on any other state. Now consider 2 qubit gates. We have the control NOT gate. What happens is, depending on the control, it knots the target qubit. So if you have 0 0, it takes 0 0 to 0 0, 0 1 to 0 1, 1 0 to 1 1. That is seen here. It flips if it flips the second qubit if the first qubit is 1. So that is seen here. 1 0 goes to 1 1, and 1 1 goes to 1 0. It flips the second qubit. So that's about the control NOT gate. We have a controlled Z gate also. It puts a minus sign if both qubits are 1. So 0 0 goes to 0 0, 0 1 goes to 1 0 1, 1 0 goes to 1 0 because uh, the Z gate acting on 0 gives you a 0. So there's no change. But when it comes to 1 1, it adds an additional phase of -1 because that's the property of the Z gate. Z gate acting on 1 gives you -1. So that's about the controlled Z gate. And there are some challenges on the way. You cannot clone the quantum states. What I mean is there exists no unitary U which clones or copies the state. Let's say you have a state A0 plus B1 and you have a dummy state 0, and you want to have a unitary which takes these two states and gives you A0 plus B1 and then A0 plus B1. So that is forbidden. That is, so it cannot clone, you cannot copy the quantum data that's forbidden using a unitary U. So when you cannot copy, you cannot broadcast. Like you want to send the same information to two different locations, that is not possible. And then you cannot delete also. You have a arbitrary state A0 plus B1, and then you have, let's say, some other alpha 0 plus beta 1, and you want to delete and say, okay, I get a0 plus b1 and a 0. So that deletion is also forbidden. So what are the applications we can think about? There's application in creation of a secret key. You know, the secret key is used to securely communicate. Let's say you have two parties A and B, and you want to establish secure communication. So there is this notion of key which both of these users have to use. And if they have the same key, then they can securely communicate. Think about n bell pairs being shared between two parties A and B. And then let's say, um, so what is the setup is as follows. You have n bell pairs. Half of the bell pairs are with A. So you have n qubits on A side and you have n qubits on the B side. And each of these qubits, let's say the first qubit of the bell pair and the second qubit of the first bell pair are, like they form a bell pair, and then you have the next set, um, the second bell pair. So second bell pair, first qubit, second qubit. Then they have a third bell pair, first qubit, second qubit. So there are n of them, and you start measuring A's side, A's qubit in the 0 1 basis normal. So what you would expect is randomly they will get projected or they'll get measured, and when you're measuring in the 0 1 basis, they'll get projected to either 0 or a 1. So you have a sequence of a random projections, either 0 1 0 whatever, but the same will follow at B also, right? So both of them have the same key and it is random, right? So both of them are now sharing the same key. This can be used on top of a classical communication. So this is where a blend of classical and quantum can be used to create secure communication. Since both of them are sharing the same string S, suppose you want to send the information X, okay? And what you will do is you will encrypt X as X XOR S, because S is the key, and you are encrypting X as X XOR S. When you send this to B, what B does is B also has the same string, right? You remember, because A and B are measuring, and whatever happens at A, same happens at B. So both of them holding the same string S. So what does B do? B performs whatever it receives. It performs an XOR operation. So X XOR S was received, and then when you did an XOR operation of S, what you get is X. So in this way, you are able to get secure communication from A to B. Both of them are now in possession of the same X. Now there's one more application which is quite famous, is this application called super dense coding. What this rests on, the assumption is that A and B are two communicating parties. A and B are sharing a bell pair. OK, and then you want to send classical bits using this quantum resource. The resources of a bell pair. OK, A and B are now sharing a bell pair, and you want to send information from A to B. You can either communicate uh, like two classical bits. So either 0, 0, 0, 1, 1, 0 or 1, 1. So whatever you want to send from A, that is two classical bits, could be 0, 0, 0, 1, 1, 0, 1, 1. That you encode. How do you encode that? You encode by performing a unitary operation on A's qubit. So I'll just repeat this. A and B are in position of a bell pair. So A and B each hold a qubit. Now you want to send information from A to B. What is the information you want to send? It's a classical information that is 0, 0, 0, 1, 1, 0 or 1, 1. Now, how do you do that? You want to send classical information using a quantum bit. Now you do something on this quantum bit. You operate either identity or X. I think, yeah, the sigma 1 is basically X, sigma 2 is Y, and sigma 3 is Z. And we have seen that what they do. So did I say that sigma 1 is X? Sigma 1 is X, sigma 1 is X, sigma 2 is Y, sigma 3 is Z. So yeah, coming back to this picture, suppose you want to send 0, 0, you don't do anything on A's qubit. OK, suppose you want to send 0, 1, what you do is you operate X gate on A's qubit. OK, and if you want to send 1, 0, you apply Y gate on A's qubit. If you want to send 1, 1, you operate Z on A's qubit. So this way you have four combinations where to send a particular information, you do some operation on A's qubit. Then after this, you send this qubit to B. Now A and so both qubits are now present at B. Now B performs a measurement. Depending on the measurement outcome, B gets to know what was communicated by A. OK, so when you measure, so when B measures these two qubits, he gets either 0, 0, 0, 1, 1, 0 or 1, 1. So whatever outcome he or she gets at B is the data that A wanted to communicate to B. So let's put the math now. Suppose there's a bell pair which is given by 0, 0 plus 1, 1 by √2, and these are the the three matrices, and identity is of course doing nothing, so that is representing the classical information 0, 0. So you pick one of these four to operate on A's qubit, and then after performing the operation, you send the qubit from A to B, and then at B performs measurement on two qubits. OK, and whatever is the outcome is the data that A wanted to communicate to B. OK, so now let's see the other side of communication. So here in superdense coding, what you used is quantum bits to send classical information, right? You send either 0, 0, 0, 1, 1, 0 or 1, 1 using these four matrices, and you are in position of quantum bits, right? So you are in position of quantum bits and you wanted to send classical bits using these quantum bits. So what did you do? You used one of the four matrices and then sent the quantum bit. The other side of the story is quantum teleportation, where you use classical bits as for communication to send a quantum bit from A to B. In superdense coding, you are sending classical bits using quantum bits. Here you are sending quantum bits using classical bits. OK, so you want to send quantum information from A to B in quantum teleportation. Here again, the resource that is used is a bell pair. So you have 0, 0 plus 1, 1 by √2. What do? You bring this qubit that you want to teleport. So there's a third qubit now. Third qubit is in state some A0 plus B1, because we have to consider the most general case. Quantum information means there is an arbitrary state A0 plus B1. But thankfully the math is such that whatever happens on the basis states, if you can figure out what happens to any arbitrary state. And that is the reason everything is linear here, and you can like project everything, whatever happens to the basis states, you can have a say to any arbitrary state. So let's see this now. The joint state, as I said, is now of 3 qubits. So you have this state that you want to teleport, and then you have a bell pair. So together there are 3 qubits. Okay, but the assumption was A and B are sharing bell pairs, right? And A is in position of one half of the bell pair, that is a one quantum bit, and B is having the other half of the bell pair, the other qubit. Now you want to send a quantum bit from A to B. Okay, so you bring an additional qubit near A. Okay, and this is what you want to teleport from A to B. So now write the joint state in such a way that this state C and A are together. Okay, initially A and B were together. Now you sort of rearrange things such that C and A are together. And it turns out that from the math that you can decompose this in 4 parts corresponding to the 4 possible measurement outcomes, or probabilistically there are 4 outcomes that is possible at A's end. Okay, because there are 2 qubits, right? So 2 qubits, when you measure, you can get either 0, 0, 0, 1, 1, 0, or 1, 1, right? So those 4 outcomes are corresponding to these 4 states, namely phi plus, phi minus, psi plus, and psi minus. Okay, so when you measure the 2 qubits that were at A, you either get 0, 0, 0, 1, or 1, 0, or 1, 1, and whatever happens. So for example, here I'm just mapping phi plus to 0, 0, phi minus to 0, 1, psi plus to 1, 0, and psi minus to 1, 1. Okay, so if the measurement outcome is phi plus, does B need to do anything? No, because B is now in position of A0 plus B1. Nothing to be done. Now, however, if at A you measure the 2 qubits and you got phi minus, okay, so the state collapsed at B is A0 minus B1, but this is not what you want, what A wanted to communicate. The A wanted to communicate A0 plus B1. So what do you need to do at B? You need to apply a Z gate on B's qubit. So how do you communicate that? You communicate that over a classical channel to B. Similarly, when you measure psi plus, the state at B is B0 plus A1. This is not what A wanted to communicate. A wanted to communicate A0 plus B1, but you have B0 plus A1. So what is the gate that you need to apply? It's the X gate. When you apply X gate on this, you get A0 plus B1, and that is what you wanted to teleport. Finally, when you have psi minus, this is what the state at B, and what is that you need to apply? You need to apply the Y gate. When you apply Y gate, you get A0 plus B1. So based on these 4 combinations, what needs to be done at B, you can communicate over a classical channel. Maybe you can encode that as 0, 0 means do nothing, 0, 1 apply a Z gate, 1, 0 you apply X gate, 1, 1 apply both gates, or Y gate, because Y is equivalent to ZX, or the product. So in this way, when you perform joint measurement on these 2 qubits at A, you can you can send that information to B, and B can apply an appropriate unitary operator to make to make that state to be teleported to B. Okay, so these are the 4 joint measurement outcomes, so either a phi plus, phi minus, psi plus, or a psi minus, depending on what you get at A. You can send that information to B and over a classical channel, and B can apply appropriate unitary operator to get the state, namely A0 plus B1. So this was about the teleportation. How much are we? Okay, so I think we have time for this one final like curious case. With this, I will end the talk. So I think, yeah, so we have maybe 5 minutes I can finish. So let's think about 3 qubits now, which are sharing this special state. This state is entangled, uh, meaning that uh, we know the joint state, but we do not know the individual parts. That is one way. The other is we cannot express this as a tensor product of 3 states, the state of individual qubits. All right, so now suppose A measures its qubit in the 0, 1 basis. OK, so A can either get 0 or 1. So if A gets a 0, what is the state of BC? It is 0, 0. If A gets a 1, then what is the state of BC? It is 1, 1. OK, now 0, 0 or 1, 1 is not entangled because 0, 0 it's a tensor product of individual states, which is 0 tensored 0. And same with 1, 1. It is 1 tensored 1. So you know the state of individual qubits now. It's a product state. It is not an entangled state. However, if you measure, if A decides to measure in a different basis, OK, in other words, in plain language, A tries to look the qubit in a different way. OK, tries to sort of measure something different. Initially, A was measuring something, and now A is measuring something different than the spin in the Z direction. Now, maybe A is measuring spin in the X direction. So that corresponds to measurement in the plus minus basis. Now, when A is measuring its qubit in this plus minus basis, you can either get a plus or a minus, right? That's how we saw. So for that, we need to express everything in plus minus basis for A. So let's do that. We are writing 0 as plus minus by root 2 and 1 as plus minus by root 2. OK, so that we know how the measurement happens at A. So with that, what we have is plus A times 0, 0 plus 1, 1 by root 2. And then we have a minus times 0, 0 minus 1, 1 by root 2. Now, when you measure A in the plus minus basis, you can either get a plus or you can get a minus. Now, if you get a plus, what happens to B and C? They are in an entangled state, right? This is the bell pair. So BC now form a bell pair. If you measure and you obtain a minus on A, then you have 0, 0 minus 1, 1 by root 2, which is again entangled. So when A does something on its qubit, that is measures in a certain basis, the outcome at B and C are totally different, right? Which is initially the first case, we have a product state not entangled. Now, if A tries to measure in a different basis or tries to measure something different, some different property, then B and C get entangled, right? So what we are trying to measure is giving us totally different results. And this is something very counterintuitive and not observed in the classical world. Whatever you do here is changing the behavior or properties of 2 different qubits B and C, and this is where there's a deviation, and this is like philosophically what we can say is what we try to when we are trying to like unravel the reality, whatever we are trying to do, right, where we're trying to measure something is still a very limited view, and it gives us only a limited picture. When you're measuring the 0, 1 basis, it is giving a limited picture about B and C. And we are measuring A's qubit in plus minus, it is giving a limited information. So together, when we have to see the whole together, then we don't know how the reality is. We can only see in parts. We can see one limited perspective or yeah, from information from only one angle. So with that, I think we can end philosophy of reality here. But what I mean to summarize is when A measures in the plus minus basis, B and C end up entangled. If A measures in the 0, 1 basis, they are not entangled. So with this, I will end today's session, today's talk. And these are some of the references I used. And if there are any questions, I can stay for a minute or maybe for 5 minutes. thank you so much for inviting me, Dr. Anusuya. It was a nice gesture. So I learned a lot while explaining. Thank you so much.
Thank you so much, Dr. Ankur, for taking out your precious time and giving such a beautiful view of the world, a new view of the world at a quantum state to all of us. Any questions? The floor is open for questions. If anybody would like to uh, ask any questions. Remember, sir, can everybody unmute themselves now?
Yes, madam. Given the permission, they can unmute.
Yeah, so you can unmute and ask if you have any questions today. Okay, maybe just one little question from me. Uh, so you talked about super dense coding where you know quantum information, classical information is transferred via the quantum way. And my question is, why is it called super dense? I mean, can we really
Okay.
transfer a lot of
Yeah,
information
it's
that way? Or?
basically okay. It's basically 1 qubit is used to send 2 bits. So in that way, uh, you're packing 2 bits in one quantum bit. So that's how it's dense in that sense.
Oh, okay, okay.
You're
That's
sending 2 using 1. That's like the
so.
idea.
One more just broad general question is, if you are, as you said, parallelly thousands of computation can happen, but your end state has to be the same. Whatever input was there, 500, then output also you get 500. But are we looking at some kind of a huge order of time saving when we are using quantum computing, or?
Okay, that's a tricky question. Not all problems. So let me put it for the record that not all problems will have that advantage.
Okay.
Simply want to add two numbers. Why you want to use quantum for that? So only certain problems which have very exponential time in classical, in like solving on a classical computer, there are solutions in quantum computing which can be faster. Certain problems which have a certain structure, which which make use, in some sense, actually the double slit experiment keeps coming uh, always. So wherever there is constructive interference, those states are amplified, and where there is destructive interference, those states do not come. So essentially, certain problems have a certain structure, and those problems which have that structure, the quantum computing can exploit that structure to give a solution. Only certain problems.
Okay, so that was the answer actually to one more question that I had. I wanted to ask you what could be a problem right now only quantum computing can potentially solve, but I guess you've given me an idea. But is there any specific problem that you
Yeah. For example, the problem of factorization.
yeah.
Like if I give you a huge number, let's say, which is 1,000 digits, 1,000 digits long number, and I want to factorize it and want to find the prime factors of that number. So if I give you this huge number, finding prime factors, the powers of like product of prime factors, let's say 2 to the 5 times 3 to the 71 times 5 to the 321, something like that. So you have a big number and you want to find the prime factors of that number. So on a classical computer, it takes exponential time, but quantum computing solves it faster than that. So so that problem has a structure. That is why quantum computing is able to exploit that structure and is able to give a solution much faster than a classical computer.
Amazing. Thank you so much. I would request for the vote of thanks.
Good evening. On behalf of Vardhaman College, I thank this opportunity to vote who have directly and indirectly contributed to this webinar on fundamentals of computing organized by our institute. I thank our resource person, Dr. Ankur Raina, who gave his vital time from his busy schedule. We are really enlightened with your knowledge and presence about computing, quantum computing, how it will be applicable for our electrical engineering students. And also heartfelt thanks to our students for active participation. So with this, we can end today's webinar. Thank you.